Hi, everybody. In this short lecture, we'll review answers to the first exam. So let's go ahead and get started. I'm cutting over to the exam file now. Let me pull it up on my screen, and we can go through the exam together. So the first question is about interpretations. And you'll remember that in logic, and in computer science really, we understand the notion of interpretations to mean an association between syntactic expressions on the one hand and semantic meanings on the other hand. And so here we have a very simple a problem about formalizing or making mathematically precise the notion of interpretations. To that end, we define two different types. A type called person var of what we can think of as variables, and we think of these as syntactic objects in our very tiny little domain here. And we define a second type of people, defining a set of three persons in particular, with names Jane, Lou, and Maria, and we take this as our semantic domain. So an interpretation then is really just a function that tells us for any given variable, x, y, or z, what person it means. Okay? So the first question asks you to define a function, aninterp, that represents an interpretation of the variables x, y, and z, such that each variable is interpreted as meaning a different person. Okay, so that's an important constraint. An interpretation under this constraint would not be valid if x meant Jane, y meant Jane, and z meant something else, maybe Lou or Maria, because then you have two variables that mean the same person. And we require that interpretations for our purposes here be such that each variable represents a different person. So we have three variables, we have three people, and we need functions that map very separate variables to separate people. Good. Okay, so in Lean and in functional algebra, more broadly, if you will, an interpretation then is a function from syntactic person variables, in our case here, to semantic meanings, which are, again, in our case here, terms of type person. So the answer looks like this. We define aninterp. This is meant to be some function mapping objects of type person var to objects of type person. And as usual, we're going to define this function by cases where there's one case for each possible value of the argument to this function. An application of the aninterp function to a value of type person var needs to return a person. And in particular, we need to decide what person gets returned for each of the possible variables. So we have three cases. The case where the argument to aninterp is x, the case where the argument to aninterp is y, and the case where the argument to aninterp is z. And now we simply need to assign return values or reduced results resulting from the application of the aninterp function to each of these variables. So the simplest thing to do is to look at the order in which these people appear in their type definition, Jane, Lou, and Maria, and just fill them in like this. So we'll, under this particular interpretation, allow Jane to correspond to as the semantic meaning of the variable x, Lou as the meaning of y, and Maria as the meaning of z. Okay, and that's it. If we wanted to, we could confirm that this function works by evaluating, for example, the application of the aninterp interpretation function to a variable like x, and the result is, aha, we get this funny thing that says hash 0. Well, hash 0 here corresponds to the first constructor, the 0th constructor, if you will, of the person type. If we use reduce here, the other interpreter built into Lean, this interpreter knows how to print out the name of that constructor properly. Okay, so we have that x evaluates to Jane, y evaluates for sure to Lou, and z will evaluate for sure to Maria, just as expected. Okay, so here we have one possible interpretation. Of course, we could have let x mean Lou and then changed other associations around, and that's what the next question asks us to do. How many such functions are there? Well, remember that each function to be counted has to associate each variable with a different person. So hint, how many choices of person do you have to associate the first variable? Well, you could let the first variable, x, be either Jane or Lou or Maria. Okay. Now when you come to the second variable, you can't use Jane because that's already used. So you have two choices for the second variable. And once you've selected, let's say, Lou for the second variable, you can't use either Jane or Lou for the third variable. So you're constrained to make the third variable Maria. Okay. And so you have three possible choices for the first variable, two possible choices for the second variable, and then your hand is forced on the third variable. And so how many different possible ways can you choose the values that go with the three variables? Well, 3 ways for the first variable. For each of those 3 ways, 2 ways for the next variable, and for each of those 1 way for the next variable. So it sounds to me like the answer is 3 times 2 times 1. In other words, 3 factorial. And that turns out to be the right answer. Okay, so the first part of the answer to this question is 3 factorial, or you could say 6, and that would be fine. Okay, that's the answer. So in part C, you're asked to define all of the interpretation functions that are possible, of which we believe there are 6. Okay, and so we can list them here. There's the one that we started with. So let's see, what did we, let's call this enter 0. Okay, now we'll make an enter 1, and what we'll do is we'll do this. We'll keep, for the first interpretation, we'll keep Jane at as the meaning of x, and we'll now take Maria as the meaning of y. And now we're constrained to have Lou as the meaning of z. Okay, so there's enter 0 and enter 1. And we have no other possibilities with Jane as the first value. So we'll now make x equal to Lou. Okay, and let's put Jane here, and we're forced to have Maria here, like that. Okay, so we have a second possibility with Lou as the value of x, and that's to have Maria here and Jane here. And finally, so that's 3. Let's make a copy of this. So that's both cases with Lou in the first slot. And finally, we can put Maria in the first slot, Jane and Lou, like this. Okay, so that's index number 4, or the 5th of our interpretations. And of course, you can see the answer now is that the final one starts with Maria here, Lou here, and Jane here, which I believe is just exactly the opposite of the order in which they were given initially. There are no other ways to assign in a one-to-one manner the variables of type person var to the values of type person. So those are the 6 or 3 factorial interpretations that we can define here. Question for you to ponder now: if we had 5 variables and 5 people, how many interpretations are there? Well, there's 5 possible values for the first variable, given that that person's out of consideration, there's 4 possible values for the second variable, and so on and so forth. So 5 times 4 times 3 times 2 times 1. That's 5 times 4 is 20. That's 20 times 3 is 60. 60 times 2 is 120. And that is, in fact, 5 factorial. So that takes us to part D, where the answer is if we have n variables and n values, and we need a one-to-one correspondence between the n variables and the n values, there is exactly n factorial ways to do that. Okay. So, very good. We call, by the way, let's suppose that we had just variables, and let's take as our semantic domain also variables. Okay, so the question is, how many different ways can you associate one variable with a different variable? So you associate Maria with Lou, you associate Lou with Maria, and you associate Jane with Jane. That's one possible association. How many possible associations are there? We think of these as essentially what we call permutations of the set of variables, where each variable gets changed into a different variable, but where all of the variables are represented in each permutation. And the number of such things is, well, you can reason about that now. Okay, the second question is about sequences, which are a fundamental abstraction, of course, in discrete mathematics and in computer science, where we use sequences, also known as lists, for all sorts of purposes. Very fundamental data structure, data type, or algebraic structure, and this asks you to reason about lists. So Lean does define a polymorphic data type called list, takes a single type parameter, which specifies the type of values to appear in a list of that type. And here is exactly how, with one tiny omission, how the list type is defined in the Lean library. And this is not just unique to Lean, this is the standard inductive definition of a list data type that you would find in essentially any functional language. And indeed, it's sort of the mathematician's inductive definition of what it means to be a list of values of some type. So we're defining the concept of a list with a type parameter, that's T, that specifies the type of the elements in a list. So list is not really a type per se, it's a type builder in the sense that you must apply the list type builder to a type T in order to obtain a type. And the type that you obtain is the type of lists with elements of type T. Try to say that again to yourself, just to be sure. When you apply the list type builder to a type T, you get a type, namely the type of lists with values of type T. Okay. Now, such a list can take one of only 2 forms. And this is really a challenging change in perspective for many people. Most people will think, oh, a list, there's an infinite number of forms of lists. There's the list containing nothing, there's the list containing 1, there's the list containing 1, then 2, then there's the list containing 1 and 2 and 3, and 1 and 2 and 4 and 5, and 7, 9, 21, 92, 54. And those are all different forms of lists. But what this definition explains is that you can just think of all of these lists in 2 cases, a base case and an inductive case. The base case is the empty list. The empty list represents a list with no values in it. Importantly, empty lists in a typed logic like Lean or in another typed logic, empty lists are empty lists of values of some specific type. So an empty list of natural numbers is a different type of list than an empty list of strings, and that's a different type of list than an empty list of Booleans, for example. Okay. So the first form that a list can take then is the empty list. And an empty list has no substructure. It has no additional parameters. There's no additional information other than that you have an empty list of values of some type. The only other form of list in this inductive definition is a form of non-empty list, where a non-empty list contains two values, a head, which is a value of type T, and a tail, which is a one smaller list, which we think of as the list remaining after you take away the head. So a list really, in this view, has only two components. A non-empty list has only two components, a head at the front of the list and then the rest of the list. Now that rest of the list could be nil, it could be empty, in which case you just have a one element list, or the rest of the list could be non-empty, in which case you have another head and an even smaller list, which could be empty or non-empty. If it's non-empty, it has a head and an even smaller list, and eventually, after some finite number of elements have appeared as head objects, you must reach the empty list at the end of the list. Now this type gives rises to an infinite set of lists, but each list in that set is itself of some finite length. Okay, we are not allowed in this framework to apply constructors an infinite number of times. So every object is built up by some finite number of applications of these constructors. So if you want a million length list, you apply cons a million times to a million head objects, and then there has to appear an empty list at the end of it all. Okay, so that's some additional background on lists. Okay, and so here I have some notes that I'm going to just erase here. We're asked, and I probably have a few more down below. I'll just erase them as we go. We're asked to define E to represent an empty list of natural numbers. And this is a little bit tricky only for one reason. If we say def E equals list.nil, we have a problem. And the problem is that there's not enough information in this term to specify the type of element in this empty list. This is ambiguous. Lean can't tell if this represents an empty list of natural numbers, or an empty list of booleans, or an empty list of strings, or an empty list of people, or an empty list of person vars. And so somehow or other we need to give Lean additional information to help it to infer what type of empty list we have here. And the easiest way to do that is to use a longhand form of the declaration of an identifier E here, and we simply say that this is going to be, we want an empty list of nat values, so we declare the type of the variable term E to be list nat, or you could say list nat like this, and then you're good. That's enough. Okay. Let me make one other comment. List.nil is polymorphic in the sense that it requires an implicit type parameter, but that implicit type parameter can't be inferred here. Now, we're not allowed to give an explicit type parameter here unless we turn off implicit parameters. So this is another way in which and this is not on the test, this is another way in which you could disambiguate the type of list.nil. The @ sign here tells Lean to turn off implicit typing, which means now if list.nil, as it does, takes a type parameter, that type parameter can now be given explicitly. Either of these answers would be fine. The one that we expect is this one, because that's the one that we covered in class, but now you know a little bit more about Lean than you did before. So again, I'm erasing notes that I typed into the test file when I covered concepts during the help sessions. Part B, use the list.cons and list.nil constructors to define L3 to represent the list containing the elements 3, 2, 1 in that order. Do this by completing the following definition. And it looked like this. Definition L3 is, and I guess that this probably said listnet. Okay. And listnet, we left you a placeholder. Okay. So what is really important to take away from this example, well, there are a couple of things, but the first is that, and I guess that I think this is probably the most important notion, is that you can build objects up in a typed functional language like this in a very, very straightforward way, no matter how complicated those objects are. And that's using what we would call top-down type-guided refinement or type-guided expansion of initially a single hole or a single placeholder. If we hover over this placeholder, the programming or lean environment here tells us what type of value is expected to go in there. It's going to be a list of natural numbers. Okay, and that tells us a lot. If we don't have a list of natural numbers already hanging around, there's only two ways that we can build one, using list.nil or list.cons. Okay, if we want to build an empty list here, we could use list.nil, but that's not the list that we want to build. Okay, it type checks, but it's not the list that we want. So the only other possibility is to use list.cons. Now list.cons takes a couple of arguments. So you can see I've made a small change to my placeholder notation here. It's exactly the same placeholder, but I've just surrounded it with parentheses. And surrounding it with parentheses is really useful because it guarantees that even if the term that I fill in here has many different parts, that whole term has parentheses around it, and so Lean will treat it as a single term. So what's going to go into the hole here? Well, I'm going to open up the hole. Here's my underscore, and the answer is list.cons. Okay? List.con, because I need a non-empty list, but list.cons itself takes two arguments, and so I'm going to go ahead and make holes for those two arguments in just the same way. And here's where the magic comes in, right? My overall answer is definitely of type listNat. You can see I don't have any type errors here because I've got a list constructor with the right number of arguments, and all I've done is leave some holes in the few places where I need to fill in some details. Moreover, Lean will tell me what types of values go in those holes. So in the first hole, the first argument to list.cons is the head of the new list that I'm building, which needs to be a value of the type parameter, the type parameter here being list nat, because we're building a list of nats. So I need a natural number here. And the natural number that I want is 3, because that's the value that I want to go at the head of the list. The second argument to list.cons is the rest of the list. And look, it itself is of type list nat. I don't want an empty list here, so I want to use list.cons to build this new list. I don't have the right number of arguments here, so I have a type error, but as long as I go ahead and provide the correct number of arguments here with placeholders in the usual way, I no longer have a type error. I just have a term that isn't yet fully developed. Okay, so here goes the head of the smaller list. So I now have a list with head 3 and a smaller list with head 2. And what goes as the rest of that list? Well, it's 2 followed by the list 1. That's a non-empty list, so I'm going to have to use list.cons here with 2 arguments. And, I'll put them in this way like this. Okay. And the same thing goes here. I need a natural number at the head of this list. Here's where my 1 will go. And now I need the rest of the list. I've got all of my list elements, 3, 2, 1. I need a second argument to cons. I don't want to add any more elements to my list. And so this list ends with list.nil, the end of the list. and now I'm good. Okay? And so in this very structured way, you don't write your list expression from left to right, holding in your mind where, parentheses need to go. Put the parentheses in first based on the constructors you're using and the arguments that they take. Then you know what type of value needs to go in each placeholder, and you just recursively apply the same concept, the same approach to filling in the holes. Okay? So I would typically not indent that, so I could write it like that. I might even put that there like that. Okay? I would put this here like that. I'd put this one here like that, and good. These don't need to be indented 2 levels, so like this and there. Okay, so and in fact, this entire thing can be put like this. So let me type it again. I'm going to just show you how quick and easy this is. If you do it like this, in this fashion, it will make your life infinitely easier. Seriously. I need a non-empty list, so that's the placeholder I need to fill in. List.cons takes 2 arguments, so that's how I type it. 1 and 2. Okay. This is where my 3 would go. This is where the rest of the list goes. It's a non-empty list, so I have list.cons. I make 2 openings for my placeholders. 1, 2. So now I have my list head 3. Now I need my list head 2 and a 1 smaller list. This needs to be list.cons. Hit enter a couple of times, go back up, put in the arguments for list.cons. There are 2 of them. Here's 1, and this is list.nil, which is the end of the list. And I'm good to go. Okay, so it's really important and extremely helpful to, again, to grow these data values kind of from the outside in. Okay, start at the top, and just like a tree, you're kind of expanding, starting at the root of the tree and expanding a tree of smaller and smaller expressions, one at a time within the larger structure of the expression tree. Okay, on part C, we want to define a function SUMList that takes any value of type list of nats, any list of natural numbers, and that computes and returns the sum of the numbers in the list. You'll have to define the function by cases and use recursion in the case where the argument is a non-empty list. Okay, so I'm going to delete what we have here and first write the definition of the type of SUMList. So SUMList is a function from values of this type, list of nats, to values of this type, nat. And if it's unclear what we're doing here, here's an example. If I have the list 5, 4, 3, 2, 1, and I apply SUMList to that list of 5, 4, 3, 2, 1, I should get back 5 plus 4, well, 5 plus the rest of the list. So that's 5 plus 4 plus the rest of that list. That's 9 plus 3 plus the rest of this list, 2, 1. That's, so 5 and 4 is 9, 10, 11, 12, 13, 14, 15. Okay, and you can see there how instead of saying 5 plus 4 plus 3 plus 2 plus 1, I say 5 plus the sum. So the sum of the values in the whole list is the head of the list plus the sum of the values in the rest of the list. Say that 5 times if you're not already comfortable with it. The sum of the numbers in the whole list is the head of the list plus the sum of the numbers in the rest of the list. Unless, of course, the list is empty, in which case there are no numbers in it, and so you need to return some value for that. So that's so we have essentially 2 cases then. In the first case, we have as an argument to SUMList, we're going to do case analysis on the first argument. If the first argument and the only argument to SUMList is the empty list, then we want to return some value. Okay, we have to decide what that value will be. It's pretty obvious in this case that it's going to be 0, but let's just leave it like that for now. And in the case of a non-empty list, look, I put parentheses in here. Okay, non-empty list, we have list.cons. That's the only other way, that's the only other form of list that we can get as an argument. It's either the empty list or it's a non-empty list. If it's a non-empty list, it has 2 components. And here we can give either new names or reuse our previous names for the components of the list. So here we call them HD for head and TL for tail. We could use HD here and TL here. Sometimes I just use H and T. Good. So if we get, good. So there's our kind of almost completed function. It just has a few remaining implementation details that we need to fill in. Right? We need an answer for when the argument to some list is the empty list. And of course, the sum of the numbers in an empty list intuitively is 0, and that's the right answer. If we have a non-empty list, then it's of this form, list.cons, applied to some value at the head of the list, and containing then the rest of the list, to which we give the name here T. So this is an example of pattern matching, where we're matching on the constructor, okay, and then giving names to the arguments that were supplied to the constructor. So I want to give you or reinforce the idea, an important idea, that this kind of pattern matching doesn't just pick a case, it also takes apart the object that we're given as an argument. Here, on the first case, we're given list.nil as an argument. It takes no arguments, and so it's just a constant term. It has no component pieces, no fields. But if we're given a non-empty list, that's a structured object. It's list.cons followed by a head and then followed by a tail. And what we need to do to compute the length of that list is to take it apart into those pieces so that we can add the first element in the list to the sum of all the elements in the rest of the list. So this kind of pattern matching in our case analysis serves a really critical function, which is to take apart the object that we're given into its pieces and to give names to those pieces so that we can use those names in defining the result that we're going to return. So this is the process that we call destructuring. If you think of a constructor as structuring an object by applying a constructor name to some arguments and then returning that term, constructor name argument 1, argument 2 in this case, then you can think of pattern matching as destructuring. If I give you that list, destructuring takes it apart into pieces. Here we match on the constructor name, but we get names for the 2 pieces of that object that we were given as an argument. Here we call them H and T. Good. Now what we need to return here for this whole is some natural number, and the question of course is, to make this function correct, we need to return the right natural number. And that natural number is going to be, well, if we're given the list 5, 4, 3, 2, 1, it's going to be 5, which is the head of the list, plus the sum of all the numbers in the rest of the list. And the whole point of recursion is that we can use the function that we're defining under certain restrictions, sum list, to compute that answer for the smaller tail. And that gives us our answer, okay? And in fact, if we wanted to, we could test this function here on this list, L3, for example. So if we evaluate the application of sum list to, for example, the empty list, we should get 0, and we do. If we evaluate the application of sum list to L3, then we should get 3 plus 2 plus 1, which is 6. And sure enough, we get 6. Okay. So there's the answer to this question here. Part D. Define a polymorphic function is empty. Okay, so our answer here, we're going to define a function is empty. It's polymorphic, so it's going to take a type argument. I'll put it in curly braces here. Maybe you started by putting it in parentheses, but we'll get to that eventually. So with what we've read so far, define a polymorphic function is empty. We can already type this much. Okay, in fact, this much. That takes as an argument a list of values of any type. So a list of values of, well, the whole point of this type parameter is that that allows us to take arguments of type list of t, where t is any type, okay? And that returns Boolean true, okay? So this function returns a Boolean, so we know that the type of the function now is list t to bool, okay? And the only interesting question left is what values should this function return for different lists, okay? So this function is going to return Boolean true, tt and leen, if the list is empty. Okay, so that gives us the first case. If we get the empty list, list.nil, then we return Boolean true. And that returns false if the list is not empty. Okay, so this is the otherwise case. Now you could think to yourself, you could overthink and say, okay, otherwise it's list.cons ht. This is not wrong, by the way, in which case we want to return false, ff, and this is a perfectly good answer. We'll take this, okay? But an even easier way to write this is just to match on anything here using an underscore. This is a pattern that matches any other case and returns false. Okay, so this function returns true if the list is empty, otherwise it returns false. And just as a kind of small comment, this kind of function, this kind of function we call a predicate function because it tells us whether a given object, here a list, has some property of interest. In this case, the property of being empty or not. Okay, so here's a predicate function that takes a list of values of any type and returns true if the list has the property of being empty. Okay, we would usually just say if the list is empty, but it's better to think now in terms of properties. If the list has the property of being empty, otherwise returns false. Okay, and if we wanted to test this, we could evaluate, for example, the application of is empty to, well, an empty list of gnats. You know, we could define an empty list of gnats. In fact, I think we defined an empty list up here, right? So in this problem right here, we defined E to be an empty list of natural numbers. So we could look at argument E here, and that should be true because E is empty. Okay, that's an empty list of natural numbers. We could also eval is empty. And I think L3 is a list of natural numbers, and that's not empty, and so this returns false. Okay, so there's a couple of test cases that you might have run yourself based on work that you had done previously on this exam. Okay, so cool. The first test on this question addressed this notion of syntax and semantics. What's an interpretation? An interpretation is a function from expressions in one type to values of some possibly other type. Question 2, the one that we just went through, is all about sequences and how they're defined and how we can manipulate them. Question 3 is about trees. So in this class, we've talked at some length about file systems as trees, but we haven't made that particular example precise yet. Okay, and so here you're asked to do that. The interesting thing about trees in file systems is that a file is either a data file with some data in it, and that's the end of it, there's no more substructure, or a file is a directory file that contains a list of 0 or more other files. Okay, so because a directory file can contain a list of 0 or more other files, in this kind of tree, a node, a directory file in particular, can contain many children, but they're all contained in sort of one list. So in one view, a node, a non-empty file, a directory file contains one object, it's a list, but that object is itself, it's a list that can contain of trees. And so recursively, a directory contains a list of 0 or more other trees, some of which can be data files, some of which can be other directory files that themselves contain other files. Okay. So question A, define a type called file, where a file is either a data file containing a single natural number, or where it's a directory file containing a list of files. Okay. We'll understand the natural number stored in a data file as representing its size in bytes. Okay, so we can already go ahead and whoops, so I'm just deleting old stuff here. So we can already go ahead and define our data file type. So inductive, file, we define file to be a type, and we provide two ways of building or constructing an object of this type. A file is either a data file that contains a number of bytes given as a natural number. So call your constructors data and dir. Here's our data file containing some number of bytes of data. Or a file is a directory file. Call your constructors data and dir. Okay, and a directory contains, and this is really the only little hard part of this problem, or hard-ish part of this problem, it contains a set of files in the form of a list of files. Okay, so the key insight here is that because list is a polymorphic type builder and file is a type that we're in the middle of defining, we can recursively or inductively include in an objective type file a value that itself is a list of smaller files. Okay? Just like a list contains a head and a smaller list, just like a tree contains, some values and smaller trees, here a directory file can contain a list of smaller files. So that's the type that we're trying to define here. Next, three values, file 1, file 2. Next, I think I asked you to define, sorry, don't know where that word went. Define three values, file 1, file 2, and I'm not sure what happened here, and file 3 of the file type as follows. Okay, so the first, file 1, is a data file containing the value 20. Okay, so I've given you this sort of template for your answers here. The first one, file 1 of type file, is going to be a value. Well, and we can see we're required to produce a value of type file here to fill in this hole. And in particular, we want it to be a data file containing 20 bytes. So it's going to be file.data is the constructor, takes an argument, and it's pretty straightforward. So file.data 20. Okay, there's no type errors here. Lean accepts this object. You could think about putting it in parentheses if you want, but you don't need to. Parentheses around an entire term never hurt. Okay, and there you go. The second file, file 2, is an empty directory file, a directory file containing an empty list of files. So here we want file.dir, and file.dir takes one argument. Okay, and what's the type of that argument? Well, it takes a list of files. And here we want the list of files to be empty, and so list.nil is going to be good enough. Now, Lean knows or can infer that this is an empty list of files because it knows that the file.dir constructor takes a list of files as an argument, so it can infer that implicit type parameter here, even though we don't anywhere on this, even though there's nothing here that explicitly names that parameter. Again, just to kind of give you a little extra lean stuff, if you really wanted to, you could turn off implicit typing with the @ sign, and in which case you give the explicit type parameter like that. Okay, good. And now this problem turned out to be, I think, probably the one that gave people the most trouble on the exam, file 3 here. And what I want you to take away from my explanation is that the way I've explained you should fill in terms of more complex types is in this top-down structured manner. Okay, so the third file is going to be a non-empty directory file containing 2 files. Okay, so we know it's going to be a directory file. So this has to be file.dir. Right, it's a directory file. And how many arguments does file.dir take? 1, of type list of file. So when I fill in an argument for file.dir, I'm done answering this question, except I have to fill in the details that go in this hole. Okay, my answer is guaranteed to be correct as far as it goes. And now I've reduced the problem of giving the entire answer to the problem of filling in a partial answer, the partial answer that remains, the rest, as it were, by filling in this hole. And now what type of value goes in this hole? It's going to be a list of files. Okay? As a list of files, I know there's only 2 possible forms. It's either an empty list, list.nil, and that would give an answer that type checks as being having the correct type. Okay, but the instructions say this list of files should be a non-empty list of files containing a non-empty list containing 2 smaller files. Okay, so I have to use list.cons here, and now just as before, I remember that list.cons takes 2 arguments. Whoops. Takes 2 arguments, the head of a list, the head of the list, and the rest of the list. Okay? And that's all I have to write. I'm still guaranteed to have a correct answer here. Okay? So the top level directory file has a list containing 2 files. The first, at the head of the list, is a data file containing the value 10. That should go here, so I'm guessing that I have to put a file here. And if I hover over that, indeed, Lean says you're building a list of files, so you better put a file here. What file do I want to put here? A data file containing the value 10. So a value of the file type has to go here, file.data10. Okay? Again, my answer is guaranteed to be correct here. There's no possibility for confusion, except, of course, that I have to fill in the rest. And here, Lane tells me, again, it reminds me really, that I need to provide the rest of this list of files. So far, I've got a list of files with 1 file at the head, and now I need the tail. Okay? And the tail is itself a list of files. And in fact, it better be a non-empty list of files because I need a second file in my overall list, a directory file. So here I need a list of files. This is where you have to think. Okay, I need a list of files. What are the possible answers here? Well, a list can be empty, and that type checks. Everything is fine, but that's not the list that I want. I want a non-empty list, so it's better be list.cons. Okay, and here, 1 argument, 2 arguments, and I go on. So, okay, so I've got my top level directory with 2 files, a data file, and now the second file I fill in here, and the second file is itself a directory file. So this has to be file.dir. Okay, And file.dir takes an argument, so I fill in a hole for that. Okay. And I need to provide it with a list of files. You see, you just really can't go wrong here. You just can't go wrong. It's very hard to go wrong here. My directory file here needs to contain a list of files. Okay. So the second is a directory file containing 2 data files containing the values 5 and 2 respectively. So here I need a list of files. It needs to be a non-empty list of files. So list.cons takes 2 arguments. Okay. I want a list of 2 files. The first one is a data file containing 5. And the second one is in the rest of the file. So the rest of the file is the rest of the list contains another file. So I can't use a non-empty list here. It's got to be list.cons with 2 arguments, the value at the head of the list and the rest of the list. The value at the head of the list is the second file in the subdirectory. That's list.data2. And now I'm at the end of the list within the directory contained within the top level directory. And so here I want list.nil. Whoops, I'm sorry, I want file.data. This is a data file. And you can see the type checker found my error. I was thinking file, I typed list, my hands just remembered list, and I immediately get feedback saying, no, I expected a different type here. Good. Okay. So what do we have so far? Well, we have a top-level directory with a list of files in it. The first file is a data file. The second file is a directory file that itself contains 2 files. So my top-level directory contains a data file and a directory file containing the rest. And what about this thing here? Okay, so what's in the rest of my my file directory? What's in the rest of this list here? You can see I'm lining up these parentheses. This whole thing from here to here is a list. This whole thing is a list. This is the list of the files in my top-level directory. Here's my top-level directory. Here's one file. It's this data file with 10 in it. The second file in that directory is this directory with all of this stuff in it. Am I done? I have a file containing the value 2. I have a file containing the value 10. I have files containing the values 5 and 2. I have a top-level directory with a data file in it and a directory file in it. I think I'm at the end of my list. This is, I need a list here, but I'm done. I guess that this would be list.nil. Okay. That's it. Okay, so filling in these kinds of answers, and by the way, sometimes I indent the very first line, but you could have even a more compact presentation like this. I selected it all and hit Shift Tab, and that just shifts it 1 tab to the left in VS Code. Perfectly good answer. Okay, so coming away from this exam, you should now feel pretty comfortable being able to write structured objects like this. You could see I got lost a little bit of track of where I was here. If you put in 2 arguments and then you spend a whole bunch of time expanding one of them, your brain is kind of going to lose track of where the other one where you are when you get to filling in the other hole. Sometimes you put a little, a little note at the end when you first list your two arguments to remind you what it is. So this is, the rest of the list of files in the top level directory. Is that true? No. This is the list of the rest of the files in the subdirectory. Okay. So here you go. Here's the top level directory. Here's the first file. Here's the rest of the files in the top level directory. This list of files contains a directory file that goes from here to here. So list.cons, first argument is a file, and then comes the rest of the list. Good. So the first file is a directory file, itself containing two files, and that's the end of the list. Okay. So you see also that when you line up your parentheses as I have here, exactly as I have here, you can always see the structure of your object. At the top level, I have file.dir. It takes one argument that goes all the way from here to here. That's a list of files. A list of files takes two arguments, a file and the rest of the list. Goes from here to here. The rest of the list in this case is a file. Goes from here to here. From here to here, rather. The file takes one argument, a list, that goes from here to here. A list takes two arguments, a file and the rest of the list. The rest of the list in this case is a non-empty list with two arguments. The first is a file. The second is a smaller list. If I really wanted to be kind of, pedantic about this, I might write it like that. Okay? And so you can see here the two arguments to list.cons just by lining up parentheses. Okay, so I really strongly urge you to lay out your definitions in this sort of systematically indented manner, that you expand from a single underscore to an application of some constructor to some arguments, each of which is on a separate line as a parenthesized underscore. That solves your problem, except now you just have to fill in those underscores. So this is what we also call a divide and conquer approach to problem solving. You solve the top level problem by figuring out what the overall answer has to be at the top level. Oh, it's a file, it's a directory file with a list of files inside of it. Okay? It's the right answer, and now all you have to do is define that list. Oh, it's a list, so it's either empty or it's a head followed by a smaller file, smaller list. So it's list.cons with two arguments, and you get the idea. This is also what we call top-down structured type-guided development, and it's an important discipline for every computer scientist to learn how to do this kind of top-down expansion guided by the types of values. Okay, so here's just some more commentary that was left over from my earlier interactions with students. Okay, and so question one was on syntax and semantics, interpretations, and really fundamentally underlying that question is this notion of how many permutations are there of 3 elements or n elements. Question number 2 was about lists. Question number 3 is about trees. And now we get back to this question of syntax and semantics, but now with a focus really on the notion that we can define a function, an evaluation function, that takes a single term and an interpretation for variables that might appear in such a term, and that yields the meaning of that expression given that interpretation. Okay, it's a very simple example of that more interesting idea, but make sure that you can repeat, roughly speaking, what I just said. We want to define a function, an evaluation function, that takes any syntactic term and returns a semantic meaning for it. Now, if your syntactic terms can contain variables, then you need an interpretation that explains the meaning of those variables if you hope to be able to explain the meaning of a term that contains variables. Okay, so here we have a very simple example of this. So in question 1, we defined a type of variables with terms x, y, and z, and we defined a set of persons representing people Jane, Lou, and Maria. We can think of the variable type person var as defining the syntax of a really simple language, one with just 3 terms, okay, each a variable expression. We can think of the person type as the semantic domain of this language, and we can think of an interpretation function like the ones you wrote above as establishing a semantics of a language by defining what person each variable corresponds to. So now you're in a position where you can set up this semantic evaluation function. We'll call it seval, and it's trivial here, but it's really important to understand how to do this in a simple case because we're going to come back to it yet again in the next lecture. So seval will take a variable of type person var and an interpretation, one of the 6 interpretations that you wrote above, and will then return the person that the given variable refers to under the given interpretation. Okay, so here we ask you to give the definition of the seval function. First fill in its type, and then fill in its definition. There was a little bit of confusion because I gave you as a template something like this, and I did help people who had trouble with this because really when we're defining functions by cases in Lean, we don't want this colon equals here. Okay, so rather we want a template that looks like this. Okay, so the type of seval, well, seval is a function that takes a person var, a variable, and as a second argument it takes an interpretation function that itself takes a person var and returns a person. Okay, and now given a person var and an interpretation, given a variable and an interpretation for the variables returns the meaning of a variable, which of course is just a person. Okay. Good. So I indicated that there's really needs only to be one case here. Let's give a name to the person var. Let's call it v. Oops. Let's give a name to our first argument. We'll call it v. Okay. Previously unused variable name will match any value of this type. We'll give a name to our second argument, an interpretation, which is a function that if given a variable returns a person, and we want to return as a result a person. So Lean will tell us, of course, that we're expected to return a person. And what we have to work with is given by this context. This whole thing here is called a sequent. It tells us what we can assume we have and what we're required to construct. So we can assume we have a function seval. We're not going to need to call that recursively here, so we're not actually going to use that. We have a variable v. We have an interpretation I. And of course, these are just names for the arguments to this function that we're defining, and we need to return a person. And what we can see is that we have a function I that if given a person var returns a person, and we have a person var right there, so if we were to apply I to v, then we would get a person, and that is what we're going to do. We apply I, which is a function from person var to person, to a value, needs to be a person var. We have a person var here, it's called v, and that's the answer right there. Okay, so that's the answer to this question. And this kind of case will come up when, as it did, for example, in the arithmetic expressions syntax and semantics that we already defined, this kind of case will arise also when we define the semantics of propositional logic, which is coming up next. Okay. Good. We can test this if we want. We'll use reduce here. If we apply s_eval to a person var like x and to an interpretation like interp5, I think it was called inter5, then we should get a person. We get Maria. If we if we go back and look at inter5 way up here, inter5 maps x to Maria. So we got the answer that we expected there. It's not a proof that the solution is correct, but it's evidence that the solution is correct. And in fact, we can reason through what we've got here and we see that it is correct. Okay, so that's that question. Let me say one last thing about this question. If you look at the type of this function, it's actually pretty interesting. Okay, and the reason that I point this out is that this kind of type is going to come up again very strongly when we really shift into a discussion of serious propositional and predicate logic. This is pretty interesting. Suppose I tell you that if it rains, then the streets are wet. Well, that looks a little bit like this if I read that arrow as an implication. If it rains, then the streets are wet. If it rains, then the streets are wet. What does this one say? Well, this one says it rains. So I know that it's raining and that if it rains, the streets are wet. So I can conclude that the streets are wet. It's raining. If it rains, the streets are wet. So the streets are wet. It's raining. And if it's raining, then the streets are wet. I can combine those two facts to deduce that the streets are wet. And this is really cool because it allows us to think about implications as functions that, if given evidence for the premise, allow us to deduce that the conclusion must be true. Okay, and this, of course, is, if you have any background in philosophy, this is Aristotle's famous syllogism called Modus Ponens, a form of valid reasoning formulated by Aristotle that he claimed was valid in all cases. If I know that if x is true, then y is true, and I know that x is true, then I can conclude that y is true. Okay, so what we're doing here in a kind of functional computing domain is now going to start to carry over very strongly when we get to thinking about predicate logic and the concept of proofs. If I have a proof that this is true, and if whenever I have a proof it's true, I can get a proof that something else is true. Whenever I have a proof that x is true, I can get a proof that y is true. And if I have a proof that x is true, then I can get a proof that y is true by applying a proof of this implication, so weird, to a proof of the premise to derive a proof of the conclusion. Premise, conclusion. If I have a proof that whenever I have a proof of this, I can get a proof of that, and I have a proof of this, then I can get a proof of that. And how do I do it? Right here. I do it by applying this proof to this proof to get that proof. So weird. But that's where we're headed. Okay, so that's not part of the exam here, obviously, but it gives you some sense of why I'm giving you problems of this kind, because they lead to some really interesting and deep insights into predicate logic and how we build proofs in a very fundamental way in that domain. Okay, so finally we're on to the extra credit questions here. Extra credit question number 1. That's hard to say. Extra credit question. Try saying that. Extra credit question 5 times fast. Good. Okay, onward. Define a polymorphic function appfold. Okay, that first line, we know what to do already. We're going to define appfold. It's a polymorphic function, okay, assuming it's in one variable, like this, okay, and this is how we start. Appfold. Good. That takes a value of type list of alpha. Okay, my type parameter is alpha here. Sometimes I use capital T's, sometimes I use alphas. They're interchangeable. As long as they're previously unused identifiers, either will do. So I have a function appfold that takes a list of values of some type, where that type happens to be lists of alpha. Okay, so I have a function that takes a list of objects of some type, where that type is itself list of values of type alpha, where alpha is given as an implicit type parameter to appfold. Okay, and that returns a list of alphas. Okay, takes a value of type list of alpha, that is a list of lists, where alpha is a type parameter, and that returns a single list of alphas, that's this type, obtained, and this now gets to the definition of how this function needs to behave, obtained by appending all of the lists in the list of lists. So here I have a list of things that are of type list. So let's sort of think about this concretely. So, if I had, what does a list of lists of natural numbers look like? If I draw lists like this, typically this would be a list of natural numbers. But now if I want a list of lists, maybe it looks something like this. And we'll put one more list in our list of lists. Okay, so there's a list of lists. And what I want this function to do is return a list, a single list, obtained by appending all of the lists in the list of lists. Okay, so append just takes two lists and glues them together. If I were to glue together all of these lists by appending them, then this is my argument. And my result should be, the result that I expect would be a single list in which all of those elements are all of those sublists are folded into a single list. Okay, so thus the name of the function, append fold. I want to fold a list of lists into a single list by appending all of the constituent lists in the argument into a single result. Okay. Now, I give you some additional information. The operator for appending lists in Lean is called list append, which can also be written using the infix operator ++. When you've gotten your function right, the test cases below should pass. So here, I define blist1. Okay. I have, let's see. I'm getting an error here on this line because I haven't defined any cases for this function yet. Okay, so blist1 is the list true, false, true. List 2 is the list false, true, false. If I construct the sequence of these two lists, well, it's the first list, true, false, true, followed by the second list. So here's an expression for these two lists appended. I could have just used append to write this this expression here, but it gave you a little challenge to figure out exactly what this expression says. And what I would expect then is if I no, sorry, I'm misguided. So here are two lists, and here's a list of lists with blist1 as the first sublist, okay, and then blist2 as the second sublist, and then that's the end of the list of lists. Okay, good. And if I fold that, then I expect to get a single list back with all the elements from those two lists reduced down into a single list. Okay, and so now let's think about our cases here. The most important insight here is that you're given as an argument a list of values of some type, and it's just a list. So don't be confused by the fact that the elements are themselves lists. You don't need to dig down that far in your mind. You just need to say, I'm given an object, I'm given an argument, that's a list of objects of some type, and that's it. Okay? So there's two possibilities. There's an empty list, okay, in which case you return some value, or you're given a non-empty list with a head and a tail. Now, it's a little bit more complicated in this case because the head is itself a list and the tail is a smaller list of lists. Okay, but let's start with the base case. We'll put an underscore here. That will help us a little bit. Here I need to return a list. So my context is that I'm given alpha is a type, and I have a function for returning a list of lists. Given a list of lists, return a list, and I need to construct and return a list. This is the list I want to return for the case where I'm given an empty list of lists. And of course I want to reduce that just to the empty list. So list.nil is going to be the answer here. Okay, no type errors on that line. And now, now this is where I am. And I really now want to start to encourage you to read these context definitions carefully. Okay? In the context where I need to fill in an answer here, I know that, and I can assume that alpha is some type. AppFold is a function that I could possibly even use that, given a list of lists, reduces it to a list. The head of my argument, H, is a list of alphas, right? Because I've broken a list of lists, list.cons, into list.cons HT, where H is a list at the head of the list of lists. It's just a list of alphas. And T is a smaller list of lists of alphas. Okay, so H is a list of alphas, and T is a list of lists of alphas. It's the tail of the larger list that I was given, possibly nil, possibly non-nil. Okay, and now I need to, given all of these assumptions, this is the turnstile character, I need to construct a value of this type, list of alpha. Okay, now how am I going to do that? Well, I want to do that by appending the list H to something involving T. But T is a list of lists, so what do I want to do with T? Well, I want to reduce that to a single list, and then I can just append H and the reduced form of T, and then I'm done. Okay, and so I want to append two values. And look, those placeholders, they play such an important role in my thinking, and in Lean and in VS Code here, you can even learn what types of values go into each of these holes, and you can see what you have to work with. Okay, so here I need to, you know what? If you bring up your app view and click on a hole, it'll give you all of this information in a way that doesn't disappear when you move your mouse. So here's my context. Alpha is a type. AppFold is an available function. And the fact that it's available means that I could apply it recursively if I need to, even though I'm in the middle of defining it. H is a list, and T is a list of lists. I want to append H, this list, like 1, 2, 3 in the example here. So I want H here, and with another list. What has to go in this second slot is another list, because list append takes two lists and glues them together. So what I want to do is I want to append this list with the list that I get by reducing or folding or appending all of the remaining lists together. And that's where the recursion comes in. And that's where the fact that AppFold is available to me in this context is so important, because I can use AppFold here. So let me close this down. I can, and whenever I have a complex term involving several pieces, I always include them in parentheses. I can use AppFold here to reduce T to a single list. And that's the answer. And look at this. Once we did the right thing here, our test case passes. Right? If I had put list.nil here, it would type check, because all I require Yeah, I could put list.nil here, but it's the wrong answer. And so I don't get back the right answer. I expected this 6-element list, and I'm just getting back nil. But if I put that back to h and look here, then in fact, I'm getting the right answer out of this function. Okay, so it's a lot of information, but these examples are really essential preparation for what we need to know pretty firmly going forward. Okay, so a really important goal of this test was just to make sure you're all over the hurdle of figuring out how to read and write these kinds of expressions. Okay, so finally, this is an extra credit question for which you were not quite prepared by what we studied earlier. It involves a notion of mutual recursion, which I explained as part of the test question. And you've seen recursion many times up until now. Mutual recursion is a really important concept as well. And mutual recursion happens when you've got objects of one kind embedded inside objects of another kind. So I have one kind of object here embedding a different kind of object, and then this object embeds more objects of this type up here. So if I have, files that embed lists of files, then I have trees that contain lists of trees. Then I want to use recursion to visit all of the nodes in the tree, but within that recursion, I need to use recursion to visit the elements of a list. And when I visit those elements of the list, I want to call the tree visiting code recursively. Then it gets a little bit weird because the recursion over trees calls the recursion over lists, and the recursion over lists calls the recursion over trees. And so you can't define either of them first because each of them uses the other. And so that leads to this notion of mutual recursion. And so this is a good example of this where, we already have a kind of mutually inductive sort of data type where a file can contain a list of, can be a directory file that contains a list. Yeah, a file is essentially a tree-like thing that's either a data file or a directory file. A directory file contains a list of files that themselves can be data files or directory files. Okay, so we have this kind of two different kinds of objects embedded inside of each other in a alternating kind of recursion. And the function that deals with objects like that is mutually recursive. So here's the question. Use your definition of files above for this extra credit question. Your goal is to define a function, du, short for disk usage, and you can try that command on, in your terminal window, short for disk usage, that takes a single file as an argument. The default argument, by the way, is current directory. And that returns a natural number that's the total number of bytes that the file takes. In fact, the real du command returns the number of kilobytes in a given file. A data file takes the number of bytes indicated in its bytes field. Okay, remember we defined data files as containing a natural number encoding the number of bytes or the size of the file. A directory file takes 5 bytes just for the directory information itself, plus the sum of the number, plus the sum of the sizes of the files in the directory. Okay, so the size of an empty directory would be 5 plus 0 for an empty list of files. Okay, so size of a directory all by itself should be 5. Size of a data file all by itself should just be the number inside that data file. But now what if you have a directory containing a data file and a directory, and that directory contains some more data files? That's the interesting question. So in our setup from above, we had a directory file that's worth 5 with a data file in it of size 10, so that's 15. Another directory, that takes us to 20, and that directory contained 2 files with 5 and 2 elements, 25, 27, so that takes us to 27 as the size of the directory file that you defined in the preceding problems. Okay. So there's a whole paragraph here. I'm not going to read it to you, but it basically says, it explains this notion of mutual recursion. And here is here is the template that I gave you for this file. And this mutual keyword basically says we're going to define two things at the same time, and they might use each other. Okay, so we can't define either of them first and then the next one second. We have to kind of define them at the same time, and that's what this mutual means. So we're mutually defining two functions, du_list and du, with du_list being a function of this type, takes a list of files and returns a natural number, and with du, the function that we really want to use being of this type, takes a single file, which could be a data file or a directory file, and tells us how much space it takes up. So let's start down here with du, which is sort of the top level function that we care about. Takes a file, returns a natural number. There's two cases here for a file. Either it's a data file containing some number of bytes n. Okay, well, in that case, we just want to return its size, n. Or it's a directory file containing a list of files. Okay, now if it's a directory file containing a list of files, well, what do we want? I think that we want 5 for the directory plus the sizes of all of the files it contains. This list of files here, we need to add up the sizes of all the files in the list. So for that, we're going to call this du_list function for the files argument. Okay. So now we need to go look at this function for adding up the sizes of all of the files in a list of files. Okay. And so there's really two cases here. Either the list is empty, in which case I think we want to return 0 because an empty list of files contains no bytes, even if, yeah. Or if we have a non-empty list of files, what do we want to return? Well, we want to return the size of the first file, which we can compute now by recursively calling du. And we want to add that to the size of the rest of the files in the list, which we can compute recursively by applying du_list to the tail. Okay. And so that, I believe, is the right answer there. We get that file 1 is 20 bytes. And file 1 is as defined earlier. By the way, if you click on an identifier in Lean and say go to definition, it'll take you right there. So here's where we defined file 1 before, and indeed its size is 20. Remember that file 2 we defined as a directory file with no files in it. Well, that should be of size 5 for the directory and 0 for the files that are in it. So let's go all the way down here and check here. And indeed, that's it. And for the overall file 3, let's go look at it again. Actually, let's use our cool new skill. Right-click, go to definition. Here's file 3. There's one directory, the top level directory. That's worth 5. Okay. Here's a data file worth 10. Here's a directory file which is worth 5 plus the sizes of the files that are in it. One of which is, did I get this right? Yes, one of which is worth 5 or of size 5, and one of which is of size 2. So that's 5, 15, 20, 25, 27. That's why we expect the answer down here to be 27. And look at that, it is. Okay. This notion of mutual recursion is really interesting, right? Because let's think about it. Let's just run over it one more time. To compute the size of a single file, if it's a data file, we just return the number of bytes that it takes. If it's a directory file, we return 5 for the directory, and now we call this other helper function du list. So this is really our helper function, okay, to compute the number of bytes in a list of files. If the list is empty, we return 0. That's natural. If it's non-empty, we add up the size of the head and the size of the tail. But to compute the size of the file at the head of the list, we call du. So du called du list, and now du list is calling du again on the file at the head of the list, which itself could either be a data file or a directory file. If it's a directory file, we return the sum of 5 for the directory plus, we call du list again to add up the sizes of the files in the list of files for this subdirectory. Okay, and so that's how this works. Okay, so those are the answers on all of the questions to this exam. What I'd like you to do now, please, is pull up your own exam. Okay, pull up your own exam, and I'd like you to go through it, and I'd like you to compare the answers that I've given here with the answers that you've given, and mark your own exam. I mean, I'll mark them, but I want you to mark your own exam. And on every single question where you got a wrong answer, I strongly, in fact, I'll even give you some credit, okay, for going through and figuring out exactly where you went wrong, okay? So there's a little bit of extra credit available for exam corrections here, okay? So I'll post a little place where you can submit exam corrections. And what I'd like you to do is not just give me the right answer, but just put in like a short little sentence explaining, where you went wrong, okay? And the goal here, again, is simply to have everybody in this class really comfortable that, you've learned the material up until now. Because what we've done up until now is super important, critical really, for the rest of the class. So we don't want to let people get by this point without having caught up. Okay, so I'll post more details about that little exam correction thing here shortly. Okay, but for now, that's it. Those are the answers to the questions on this exam. I hope you enjoyed taking the exam. I hope it didn't feel too high pressure for you. I helped everybody who asked for help, I believe. There were a few people who had medical and other issues that meant they had to turn in exams a little bit late. I have them, and we'll be getting back to you shortly with grading results. Okay, so for now, that's your exam review. Thanks.